Okay, so today's notes, more phantoms. This time it's phantoms for mean, though. Like a phantoms for proportion, it should remind you of a panic, or it's going to have some of the similar components to a panic, and then some of it will be new. So we're just going to do the entire process. Here's our context. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. A dissolved oxygen level below 5 puts aquatic life at risk. Can we conclude that aquatic life in this stream is at risk? Carry out a test at the alpha equals 0.05 significance level. Does this sound familiar to you? Should. We've already seen this data. In fact, you constructed a confidence interval, I believe. Okay, so starting with our parameter. This is hopefully clearly a case for mean, not proportion. So I'm going to say let mu be the population mean dissolved oxygen level in this stream. Then we move on to our null and our alternative. Both are going to be in terms of mu. We want to know, is there evidence that aquatic life is at risk? Bless you. Is there evidence aquatic life is at risk? Aquatic life is at risk if our dissolved oxygen level is below 5. So HA is mu is less than 5. HO is mu is equal to 5. Next, we're going to check our assumptions. It's the exact same assumptions as it would be for a panic. First one is random. In this case, what does random mean? What does random refer to?
Randomly chosen locations.
Yes, a randomly chosen sample. This is a survey, not an experiment. So is it a random sample? I'm going to say yes. And that is stated, like Maddie said, randomly chosen locations. Then we've talked about the 10% rule. In this case, 10% rule doesn't need to be checked. Anybody remember why? Maddie?
Because there are an infinite amount of locations on a stream.
Yes, it is an infinitely large population. So you don't need to write this, but I'm going to write it just because it will be helpful in your notes, hopefully. Unnecessary because we have an infinite population. Third assumption, the one that is specific for mean, is what? Which distribution is normal? The what? I think someone said it right, someone said it wrong. Your options are sample, sampling, population. Which one do we need to be normal? Sampling. Sampling. We want to know, is the sampling distribution normal? First way to check that is we are told the population is normal. That's not the case here. What is the second way to check this? Central limit theorem. That would be a sample size greater than 30. That's not the case here. So instead we have to look at the sample. Put that data in your calculator, please. And then you're going to construct a graph of some type. I normally do a histogram. You can also do a box plot, either one. I believe if you do a histogram, it looks something like that. Yeah? Thank you for the few of you that nodded at me. And then we need to write a sentence. Some of you did this well on the test, some of you did not. What is this a graph of? The sample. So we will say because the sample does not show extreme skewness or outliers, the sampling distribution is approximately normal. I cannot stress enough to you, this is not necessary for every single problem. If the population is normal or if the central limit theorem applies, you should not have a graph of any type. Now, we've done so many examples where you have to look at the sample because this is hard for students. This is not normally what comes up on the AP test, though. The AP test very rarely, if ever, has you put data into your calculator. Because if you put a number in wrong, you're going to get the problem wrong. So more likely on the AP test, you are more likely to get a problem where the population is normal or the central limit theorem applies. So just be mindful of that. Questions before we keep going? Okay. So for our n, this is a lower-tailed one sample hypothesis test for mean. Using alpha is 0.05. And then proportion, I said we got to choose if it's Z or T. Same thing with mean, Z or T. It's the same as with a panic. We use Z if we have the population standard deviation, which is pretty much never, or we use T if we have a sample standard deviation. In this case, we're going to calculate a sample standard deviation. So we are going to use T with 14 degrees of freedom. 14 degrees of freedom, and it's n minus 1, like with a panic. One quick note that's not a big deal, but I want to tell it to you anyway. I don't know why your book differentiates. Your book, for some reason, calls it a large sample hypothesis test for proportion, but one sample for mean. I would just say one sample all the time. I wouldn't differentiate the large versus one. If you want to, that's fine. But you can say one sample for mean, one sample for proportion. Test statistic. Okay, so it's going to be the statistic, which is x bar. We are subtracting the mean. And we are dividing by the standard deviation. This is the standard deviation, like with panic. In the panic formula, it was S over root n. Now, alternately, the formula could be Z equals x bar minus mu over the population standard deviation over root n. You would be using Z if you had the population standard deviation. Like I've said, I've never seen a problem where that's the case. We need to calculate x bar and S using the calculator. So right now, do your 1 var stats, please. And hopefully we all get the same numbers. I get an X bar of 4.77. Beautiful. Mu is 5. That's from the null. Standard deviation, remember that you're using S, not sigma. So I get about 0.94. Okay, so please calculate this. And I believe you get about negative 0.94. Yeah. Okay. So now we are going to draw our normal curve. Our test statistic of that negative 0.94 goes right here, and it is a lower-tailed test. Now for standard deviation, this is the one that students tend to mess up. You are not using 0.94. This figure is the sampling distribution. So your standard deviation is everything that's in the denominator, which is about 0.24. Okay, so now we are calculating the probability that t is less than or equal to negative 0.94. Here is something that is new. We are not going to use normal CDF because this is not z. So we are not going to use normal CDF because this is not z. Instead, if you go to the same spot where you would normally find normal CDF, instead, you're going to use what's called Tcdf. Tcdf. It works similar to normal CDF, but not exactly the same. And that's because a normal distribution is based on a mean and a standard deviation. A t distribution is based on degrees of freedom. So the order that you put into Tcdf is the lower bound. In this case, negative 1 times 10 to the 99th. The upper bound, which is negative 0.94. And then degrees of freedom. And then degrees of freedom. And when you do that, you should get a p-value of about 0.18. So this one only has 3 numbers you're putting in: lower bound, upper bound, degrees of freedom. And again, that's because a t distribution is based on degrees of freedom, not mean and standard deviation. Mary?
So finding the p-value goes in the O step instead of the T step?
Wherever you want it to go, yeah. I'm not very consistent with it. Sometimes I put it in T, sometimes O, sometimes M. But yeah, wherever you are more comfortable. Okay, here's what I would like. We're gonna take a 2-minute pause. I would like you to finish this, please. So write your conclusion. Both the reject or fail to reject, And then write a conclusion for the p-value, please. Okay, so here's my conclusion. In N, you should have shown that your p-value is greater than alpha, so we fail to reject. Based on my analysis, I fail to reject the null as there is insufficient evidence to believe the population mean dissolved oxygen level is below 5. Hopefully you included units. And then did you answer the question? The question asked, does it appear that aquatic life is at risk? So we should have said no, doesn't appear that aquatic life is at risk. For the p-value, 0.18 is the probability of a sample mean of 4.77. Ooh, I forgot something. 4.77 or smaller if the population mean is 5. Okay, this or smaller should follow your figure. So less than, hence it's smaller. If that confuses you, if you're not sure whether it's smaller or bigger, the kind of cheater way to do this is you can always just say more extreme in any case, and that will work as well. So this should be pretty similar to a panic. What's nice about mean compared to proportion is there isn't the small differences in symbols like there is with proportion between panic and phantoms. So I think there's less to mess up, theoretically. Any questions for me before you all try one? No? You're ready to try one? Okay, before I show you the example that you are trying, do you remember talking about how on the AP test there's 6 free response questions and the last one is worth more and it's longer and it tends to be something you haven't learned before? It's called Investigative Task. That's what you're going to be doing. The first part is phantoms. It's exactly what we just learned. The second part is the investigative piece. This is the example that you are doing. It says a bottle filling machine. It should be the very next question. This has 2 pages. It's parts A and B, so you are doing both. Okay? Here is the answer to part A. To part A, you should have had a 2-tailed test. Did you notice that it told you that all the conditions were met? You didn't actually have to check them. Something I'm going to be very picky about, though. If I asked you to check the conditions, how would you check the approximately normal sampling distribution one? How is that one met for this context? Is it stated that the sampling distribution is normal?
It's stated
That the population is normal. So what sometimes students will do is they'll say sampling distribution normal? Yes, stated. That's not the case. It is stated that the population is normal. So I would expect you to say the population is normal, therefore the sampling distribution is normal. Should have gotten a p-value of 0.324. Remember I said if, with a 2-tailed test, wherever your test statistic is, shade away from the center. So in this case, that would be lower, and then you would double. You should have compared to alpha and said, I'm going to fail to reject the null. Did we do okay with that? Okay. Can we take a look at part B then? We're going to read it real quick, and then I will give us a hint. To determine whether this sample of 4 bottles provides convincing evidence that the standard deviation of the amount of juice dispensed is greater than 0.05, a simulation study was performed. In the simulation study, 300 samples, each of size 4, were randomly generated from a normal population with a mean of 12.1 and a standard deviation of 0.05. The sample standard deviation was computed for each of the 300 samples. The dot plot below displays the values of the sample standard deviations. That is a sampling distribution. Every dot represents a sample of size 4, and it's the sample standard deviation. So then the question, use the results of this simulation study to explain why you think the sample provides or does not provide evidence that the standard deviation of the juice dispensed exceeds 0.05. This is not asking for your own opinion. This is asking for a numeric argument. So is there evidence suggests a hypothesis test. A hypothesis test is determined by a p-value. So we need to ask ourselves conceptually, what does a p-value represent? Because we don't have a formula here that we can use to calculate a p-value. So what, in general, does a p-value represent? It's a probability, but a probability of what? Hannah? Okay. It's the probability of the sample we got, or more extreme, if the null is true. Now, it already tells us that the null is true because it already tells us that that's what we're assuming because it says that this sampling distribution comes from a population with a standard deviation of 0.05. So that is the part that's saying the null is true. What is the sample result that we got? It's not here. It's earlier in the question. We're talking about standard deviation. This is standard deviation. What sample standard deviation did we get? What was it? 0.085? So we want to know standard deviation exceeding, so that tells us that this is an upper-tailed test. So what you need to do is estimate a p-value for an upper-tailed test where the sample result you got is 0.085. So estimate the probability for this simulation of a sampling or of a sample standard deviation of 0.085 or bigger, since it's upper-tailed. Take 2 to 3 minutes, and then we're going to come back together and grade this. Okay, so like I said, the whole idea here is find the probability of the sample that we got, or one more extreme, if the null is true. So you are trying to find the probability, or estimate the probability, of a sample standard deviation of greater than or equal to 0.085. That's what you need to estimate. On the simulation, that happens right here. That happens 12 times out of those 300 samples, which gives you a probability of 0.04. That is the p-value that you would use to make your conclusion. So in this case, p-value is small. So yes, there is evidence that the standard deviation exceeds 0.05. How many people got that? Yeah, I expected it to not be too many. Questions on that? I don't know if you care. Here is College Board explaining what I just said. So out of the 300 samples, we only got a value larger than 0.085 12 times. So again, you get a p-value of 0.04. You will be giving 4 grades. 3 for part A, 1 for part B. Here's why this is a little bit harsh. Part A gets 3 grades. They are all essentially correct or incorrect. That's it. There's no in between. The first grade, as you can see, is does the person have the correct hypotheses? They need to have the correct symbol, inequality, and number. And if they did that, they get essentially correct. Everything else is incorrect for that first grade. Second grade, they have to identify the correct test by name or formula and include work. Here's what they need to get essentially correct. They need everything that I'm about to say. Even one mistake means it's completely wrong. Then you need to say one sample, hypothesis test for mean. They need to give alpha. They need to say using T. They need to give degrees of freedom. The formula needs to be correct. So that's x bar minus mu all over s over root n. They need to get the correct test statistic, negative 1.176, and the correct p-value of 0.324. All of that gives them essentially correct. If they even have one symbol wrong, it's incorrect. And then the third grade in part A is a correct conclusion in the context of the problem. I fail to reject, there's not enough evidence to believe, blah, blah, blah. So that should be 3 grades. We got 3 grades so far? Okay. Section 4, so this is part B. In part B, they can get partially correct. The person gets essentially correct if they find the correct p-value from the dot plot and give a good conclusion. If they have the correct p-value, but the conclusion is weak, wrong, or missing, it's partially correct. Everything else is incorrect. So probably most of us would have gotten incorrect. So the person should have 4 grades. Did anybody get a P on the last one? Okay, so then here's how the grading is going to work. Every E is 1 point. P is half a point. You cannot get, though, a 2.5. So let's say the person had E, E, I, P, which is 2.5. The grader would have to determine whether to round up or down based on the strength of the response. So right now, give the person a total out of 4, hand it back, and provide some constructive feedback and positive feedback.